Today we'll cover the greatest number of roots theorem. Let R be some integral domain, and let f be some non-zero polynomial over this domain, and let the degree of f be equal to n, which is some natural number. Then the polynomial f has at most n roots in R. Also notice that it is very important that R is an integral domain. If it were a mere ring, then it generally wouldn't hold. Right, so the proof is by induction on n. Proof. So by induction on the degree of f, which is n, the base case. Right, so n is equal to 0. Then f is some constant non-zero by assumption, non-zero polynomial, and thus it has no roots. Right, a line parallel with the x-axis doesn't intersect it, unless we're considering projective geometry, but that's a completely different topic. Now, assume the claim holds for all polynomials of degree up to n. Now, the induction step. So, suppose f is of degree n plus 1. Either it has no roots, in which case the claim holds, in which case, okay, or it has at least one. At least one root. Now, call this root n. Call this root a. By the previous theorem, that is the polynomial factorization theorem. So, the polynomial factorization theorem, f is equal to x minus a times g for some polynomial g of degree n. Well, alright. Now, if g has no roots, then there is precisely one root and the claim holds, because n is equal to at least 1, right? Or, so either no roots, no other roots, or either g has no roots, in which case great, or there exists another root of g, or rather exists a root of g, call it b. Then we have f of b is equal to b minus a times g of b, and because b is the root of g, this is equal to b minus a times 0, and this is 0. Now, because we are dealing with the integral domains, this means that either, well, b minus a is 0, or g of b is 0, or in other words, g is the root of b is the root of g. Now, if this holds and this doesn't, this means that there don't exist any more roots. There are only two again. This actually isn't even important because f is equal to b minus a times g. G has at most n roots, and this is one root, right? So thus f has at most n roots, n plus 1 roots, which finishes the induction step, and we conclude the proof.